Hi, we are ME Team 37. We are investigating the flow characteristics of a catalytic layered screen reactor. I am Austin Gray.
I'm Roger Lynn.
And I'm Matthew Tyler.
Our advisor for this project is Alexei Polodnenko. Our sponsor from Precision Combustion Incorporated is Jeff Weissman. The objective for this project is to determine the pressure drop, outlet flow velocity, and outlet flow distribution of PCI's catalytic reactors for inlet flow velocities ranging from 1 to 10 meters per second. They have two primary configurations of these reactors, shown on the right two pictures. The top right picture is a linear stack of mesh screens. The bottom picture is radial flow through a roll of mesh. It goes in the inlet. It's plugged at one end, which forces the flow radially outward through the mesh roll. At the bottom middle, we have a close-up view of the mesh screen material. Our first primary configuration is the 1D flow configuration. Shown in blue in the top middle picture is where our test section lies. This is where our stack of mesh screen is. Shown in red is a close-up of our testing section. And below, on the left, is our first measurement. This is where we measure the inlet axial velocity right before the flow goes into the mesh screens. After the flow leaves the mesh screens, we measure the outlet axial velocity, shown in the bottom middle. And finally, on the bottom right, we measure the pressure drop across the mesh screens with a manometer. Our second primary configuration is the radial flow configuration. Shown in red is the radial test section, and shown in yellow on the right picture is the mesh roll. That right picture shows the cutaway view of our radial test section, where we have a flange, a 6-inch pipe, the mesh roll, and the backstop to stop the flow from going out the end. Our first measurement on the bottom left is our inlet axial velocity, right before the flow goes into the mesh roll. Our bottom middle picture is the outlet radial velocity. This is where we measure the velocity along the length of the mesh roll as it goes radially outwards out of the end. And finally, we have our pressure drop.
Here are the graphs created from our testing data. The two graphs show the relationships between inlet velocity and pressure drop, as shown on the left graph, and inlet and outlet velocity, as shown on the right graph. The equations found from the trend lines and the pressure drop versus inlet velocity graph are important, as they are used in finding the highlighted terms of the modified Darcy's law, shown below. These terms are then used in ANSYS to define parameters used in the simulations. The rest of the parameters in the equation are found using properties of air and the mesh. Here's the ANSYS model for the linear configuration for an inlet velocity of 10 meters per second, created using the parameters mentioned before. We see the pressure drop across the mesh is about 460 pascals, as shown from the color distribution in the model above. This matches the pressure drop found from the testing data, as the pressure drop is about 414 pascals, as shown in the bottom right. The same process for the linear configuration was tried for the radial configuration. However, the equation for the pressure drop versus inlet velocity was linear. This creates a problem with the parameters used to create the ANSYS simulation, as they require a quadratic equation to find correct parameters, as shown again from the modified Darcy's law. Here we see the pressure drop and velocity models from the simulation, and the simulation thinks that there's no flow going through the mesh, and this is indicated by the blue, where it shows low to no flow velocity. This is due to the parameters found from the linear data, and reasoning for these incorrect parameters will be discussed after the next few slides.
Results for our linear configuration are as followed. The correlation above was given to us by PCI to predict the pressure drop for each velocity, as well as some constants. As you can see below in the red, this was the pressure drop we'd expect for our number of meshes and for the velocity. In blue and green, we have our trial data, which shows that it is a very good fit for PCIs, proving that PCI's initial estimate was correct. Now onto the issues with our radial configuration. As Roger talked about previously, we could not get good constants for our ANSYS. This was probably due to having a lot of flow leaving in the beginning of the mesh, as you can see with the graph below. We believe this was due to an issue with creating a good seal with our mesh and our flange, meaning that air was able to flow around the mesh roll rather than go through it. When we were trying to alleviate this issue, the mesh roll began to unroll and cause a small blockage in the beginning of the mesh, exacerbating this issue. And because of this, and with the constant pressure drop, which we were not expecting, we could not get good constants for our ANSYS, and then we're not able to confirm our initial hypothesis of a bell curve. Recommendations for PCI. Ambient temperature and the temperature of all components must be maintained within 0.1 degrees Celsius to obtain useful data. The assembly of the mesh stack is critical to get uniform flow. The orientation and compression of the mesh must be consistent, as well as the diameter of the mesh circles must match the pipe diameter to avoid any concave meshes. If we were to do this experiment again, we would create 2 backstops for the radial section, having one of the backstops be able to seal well with the flange to avoid any issues with air escaping instead of going through the meshes. And for the linear testing, we would create a washer to allow a backstop for the meshes to be loaded into consistently and to be able to have the same amount of compression.